Okay, we need to find the exact values of the modulus and argument of 2p over w squared. Okay, so here from here, right, very quick recap on what we taught before during lecture. That remember when we are talking about the argument of z1, z2. Okay, for example, two different complex numbers, right? This is the same as the argument of z1 plus the argument of z2, right? And you are talking about the modulus of z1, z2. But this is the same as the modulus of z1 times the modulus of z2. Okay, so the argument of a product is the sum of the arguments. The modulus of a product is the same as the product of the modulus. Okay, and if I'm talking about argument of z1 over z2, argument of a quotient is the same as the differences between the argument. Okay, this let's do is like a quotient law. Okay, because simply in your complex number, you write an explanation for your arguments are the powers, right? They're the powers REI theta. Okay, and z1 over z2 is just equals to the modulus of a quotient is the same as the quotient of the modulus. This is for a quick recap. Okay, then let's look at this. Alright, we need to find the modulus of an argument of 2p w squared. Okay, so quickly, right, 2p w squared, if we talk about the modulus of 2p over w squared, this is the same. We take out 2 mod p over mod w. Okay, we take out the square as well. Okay, right? And so you can see that this is just equals to 2. Let me erase the extra stuff. Okay, 2 times 3. Right, modulus of p is just 3. Modulus of w is 2 as well, so it's 2 square. So it just equals to 6 over 4, which is 3 over 2. 6 over 4, which is 3 over 2. What about the argument of 2p over w squared? So the argument of 2p over w squared, you can say that this is the same as the argument of 2p minus the argument of w squared, correct? And argument of 2p, we can say that this is the same as the argument of 2 plus the argument of p, right? So you can see this is so fun. We can actually do multiplication just with the argument. Argument of w squared is the same as 2 times the argument of w. Remember, you recall in the notes, argument of z power n is the same as n of argument of z. Okay, and argument of 2, what's argument of 2? Okay, so if you recall in the Argand diagram, where is 2? 2 is just on the positive real axis, right? So what's the argument of 2? Argument of 2 is just 0, right? What's the argument of p? 7 pi over 8, right? And what is the argument of w? The argument of w is a negative 5 pi over 8, so it's negative 2, negative 5 pi over 8. Alright, and simplifying this, your answer just comes out to be, okay, let me just rewrite it on the left hand side. Okay, the argument of 2p over w square is the same as 0. Argument of 2 plus the argument of p minus 2 times of argument of w. Okay. And the answer turns out to be 17 pi over 8. Okay, so we verify that this again is not in the principal range, so we do not want it. The answer is too big, we minus multiple of 2 pi, right? So let's minus 2 pi, and the answer just turns out to be pi over 8 after subtracting 2 pi. Okay, so this is the argument of 2p w squared. So we can say that 2p over w squared, right, can be written in the exponential in the polar form, right? We know that the modulus is 3 over 2, so you can say it can be written as 3 over 2 r cos theta plus I sine theta, right? This is in the polar form. In the exponential form, we can also say that it can be written as r 3 over 2 e to the power of I pi over 8. Okay, so I'm just going to keep it in this form because it might be useful later on. Okay, then next I need to find the smallest positive value of n such that 2p over w square to the power of n is purely imaginary. Okay, it's purely imaginary means what? It means that the real part is 0, huh? Okay, so let's look at this. What do we know about this complex number? So it's 2p over w square. So you see, it does look kind of familiar. This portion looks like part 1, right? So you know, always see the big picture, try to link your questions together. This looks like part 1. So 2p over w square, 2p over w square, this is our 2p over w, right? So 2p over w square to the power of n. It seems as though I'm taking this whole polar number to the power of n, right? Or I can say it's this to the power of n, right? But you can see that, you see, you're able to manipulate, right? Actually, right, you can write it this way. This is the same as 3 over 2 to the power of n. This is the same as I n pi over 8. Am I right? And you can say this is just another complex number. This is another complex number where your modulus, right, is 3 over 2 power n, where your argument, okay, is just, the theta is just n pi over 8. Okay, so it's easy because here the argument, or the knowledge that we use from the lecture question we have told you before, the comprehension note. You want to find the argument of z power n. This is just n of the argument of z. If you want to find the modulus of z power n, this is just n power of the modulus of z. Okay, so that's why you can see that in this case, part 2, right, is actually linked to part 1. 2p over w square. Okay, here, this is nothing but 3 over 2 to the power of n. Okay, I'm going to write in polar form, right? It's just equals to the polar form is cosine pi over 8, so it's cosine n pi over 8. Okay, I hope you can get this part up. This is actually, again, nothing but using these two formulas. Okay, n pi over 8. Right? So this from this portion. Is from this portion. I just basically put this in polar form. Okay? And you can see that now I'm going to try to show you, okay, what does the real part of this complex number. It looks like 3 over 2 power n cosine n pi over 8 plus I 3 over 2 power n sine n pi over 8. So let's say if you are not clear, you can just look at this complex number and say, hey, this is the real part. Alright, if you want the complex number to be completely imaginary or purely imaginary, it means, right, to be purely imaginary, it means what's the real part? The real part must be equals to 0, correct? It means we want the real part to be equals to 0. So simply what we do is we try to equate this to 0 now. 3 over 2 power n cos n pi over 8. Let's equate this to 0 and we see what we get. Okay, let's see what we get. Okay, and cos 3 over 2 power n, this is non-zero, so we can just cancel this away. I mean, it's useless, right? So cosine n pi equals to 0. So remember, okay, okay, I hope you remember your secondary 3A math or GH math, right? Cosine, this is the cosine graph, right? Okay, this is the portion. Where is the cosine x? Right, where's the portion where it's equals to 0? It's pi over 2 and 3 pi over 2. Okay, so this is just means that n pi over 8. Alright, the basic angle is it could be equals to pi over 2, 3 pi over 2, right, so on and so forth. If you want to go backwards, it can also be negative 3 pi over 2, negative 3 pi over 2. It can also be negative pi over 2. Right, so there are many possible values of n pi over 8. Okay, n pi over 8. Remember, we are solving for n. We want n to be positive. So n pi over 8, n pi over 8, right, could be, example, negative 3 pi over 2. So we're just going to list a few examples. Negative pi over 2. It could be pi over 2. It could be 3 pi over 2. Correct? So if I multiply all by 8, the idea is I'm going to solve and I want to find the value of n, right? So that means we need to reverse we need to take away the pi, we need to take away the 8. Okay, so if I cancel all by pi, that's possible, right? So I can say that n over 8. Okay, I'm going to go slow. I mean, I don't want to, for those who are very fast in algebra manipulation, you may irritated by my slow working, but that's okay, because you can just fast forward the video. Okay, n is just equals to negative 3 over 2. So if I multiply by 8, what will I get? Okay, you can see that if I multiply by 8 on both sides, I get negative 12, negative 4, positive 4, positive. So what's the smallest positive value of n? You can see, right? Actually, it just equals to 4. Oh, so the smallest plus the smallest. Okay, so I conclude with an answer. The smallest positive value of n is equals to 4. Okay, by simply looking at the equation, we equate the real part to 0, because the question tells us that it's purely imaginary, so it means the real part is 0. While solving for the real part of 0, we solve for the value of n. While solving for all the values of n, we find the smallest one, the smallest positive one, which is 4. Okay,